Grounding and bonding are critical aspects of electrical safety, ensuring that electrical systems function correctly and protect individuals from electrical hazards. Several codes and standards govern these practices, including the National Electrical Code, or NEC, and the Kentucky Electrical Code, or KEC. Let's explore these codes and the key sections related to grounding and bonding. Firstly, understanding the NEC and KEC is paramount. The NEC, published by the National Fire Protection Association, or NFPA, is a widely adopted standard for electrical installations in the United States. The Kentucky Electrical Code, or KEC, adopts the NEC with some state-specific modifications. Therefore, compliance with both codes is essential in Kentucky. One should consider Article 250.50 of both the NEC and KEC, which addresses the grounding electrode system. This section outlines the requirements for establishing a low-impedance ground connection to earth. The grounding electrode system typically includes various electrodes, such as metal underground water pipes, concrete-encased electrodes, ground rings, and ground rods or pipes. Secondly, NEC and KEC Article 250.52 specifies the requirements for grounding electrodes. Acceptable grounding electrodes include metal underground water pipes that are in direct contact with the earth for 10 feet or more, the metal frame of the building or structure, concrete-encased electrodes consisting of at least 20 feet of 1/2 inch or greater electrically conductive reinforcing steel or copper wire or cable encased by at least 2 inches of concrete, and ground rings consisting of a bare copper conductor not smaller than 2 American wire gauge or AUG, encircling the building or structure and in direct contact with the earth at a depth of not less than 2.5 feet. Rod and pipe electrodes should not be less than 8 feet in length and shall consist of electrodes of pipe or other metal that are not smaller than 3/4 of an inch trade size and shall be galvanized or otherwise metal coated for corrosion protection, or shall consist of stainless steel or copper. Rod and pipe electrodes of steel or iron shall have the outer surface electrically conductive, such as galvanized. Non-ferrous rods or their equivalent shall be listed and shall be not less than 1/2 inch in diameter. All grounding electrodes that are used shall meet the installation requirements outlined in the code. Thirdly, NEC and KEC Table 250.66 provides guidance on the size of the grounding electrode conductor for alternating current, or AC, systems. This table specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor connects the grounding electrode system to the equipment grounding busbar in the service equipment. The size of the grounding electrode conductor is crucial for effectively carrying fault current back to the source, facilitating the operation of overcurrent protective devices. Additionally, it's important to consider other resources like the cable television grounding standards, which offer guidelines specific to cable television systems. These standards address grounding and bonding requirements for cable installations to ensure safety and prevent interference. One should also consider IEEE Standard 142-2007, commonly known as the Green Book, which provides recommendations for power systems grounding. This standard covers various aspects of grounding, including system grounding, equipment grounding, and static grounding. It offers detailed guidance on designing and implementing effective grounding systems in industrial and commercial facilities. Let's delve deeper into NEC Article 250.50 on grounding electrode systems. This article emphasizes the importance of creating a low-impedance path to ground for fault currents. A low-impedance ground path ensures that overcurrent protective devices, such as circuit breakers and fuses, operate quickly to clear ground faults, minimizing the risk of electrical shock and equipment damage. Article 250.50 outlines the requirements for interconnecting different grounding electrodes to form a comprehensive grounding electrode system. This interconnection ensures that all available grounding electrodes contribute to the overall grounding effectiveness of the system. Common grounding electrodes include metal underground water pipes, which must be supplemented by an additional electrode, the metal frame of the building or structure, concrete encased electrodes, ground rings, and rod and pipe electrodes. Now let's explore NEC Article 250.52 on grounding electrodes. This article specifies the types of grounding electrodes that are permitted by the code. As previously mentioned, acceptable grounding electrodes include metal underground water pipes, the metal frame of the building or structure, concrete encased electrodes, ground rings, and rod and pipe electrodes. The code provides detailed requirements for the installation and connection of each type of grounding electrode. For example, metal underground water pipes must be in direct contact with the earth for at least 10 feet and must be electrically continuous. Concrete encased electrodes must consist of at least 20 feet of 1/2 inch or larger reinforcing steel or copper conductor encased in concrete. Rod and pipe electrodes must be at least 8 feet long and must be driven into the ground to a depth of at least 8 feet. Now let's break down NEC Table 250.66, grounding electrode conductor for alternating current systems. This table provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. The service entrance conductors are the conductors that bring power from the utility company to the building or structure. The larger the service entrance conductors, the larger the grounding electrode conductor must be. This is because larger service entrance conductors can carry more fault current, and the grounding electrode conductor must be able to safely carry that fault current back to the source. The table specifies the minimum size of the grounding electrode conductor in American wire gauge or AUG, or in thousands of circular mils or KEC mil, based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 AWG copper, the minimum size of the grounding electrode conductor is 2 AWG copper. If the service entrance conductors are 250 KEC mil aluminum, the minimum size of the grounding electrode conductor is 2 AWG copper. It is important to consult the table carefully and select the appropriate size of the grounding electrode conductor to ensure compliance with the code. Let's also consider the cable television grounding standards. These standards provide specific guidance on grounding and bonding cable television systems. Cable television systems can be susceptible to ground loops and other grounding-related problems, which can cause interference and even electrical shock hazards. The cable television grounding standards address these issues by providing requirements for grounding the cable shield, bonding the cable system to the building's grounding system, and protecting against voltage surges. One should also note that the Institute of Electrical and Electronics Engineers, or IEE, Standard 142-2007, the Green Book, provides detailed recommendations for power systems grounding. The Green Book covers a wide range of grounding topics, including system grounding, equipment grounding, and static grounding. System grounding refers to the method of connecting the neutral point of the electrical system to ground. Equipment grounding refers to the method of connecting the non-current carrying metal parts of electrical equipment to ground. Static grounding refers to the method of grounding equipment to prevent the buildup of static electricity. The Green Book provides detailed guidance on designing and implementing effective grounding systems for each of these applications. In summary, compliance with the NEC and KEC, along with consideration of other relevant standards like the Cable Television Grounding Standards and IEE Standard 142-2007, is essential for ensuring electrical safety and proper system operation. Understanding the requirements for grounding electrode systems, grounding electrodes, and grounding electrode conductors is crucial for electrical professionals working in Kentucky and elsewhere. By following these codes and standards, you can help to protect people and property from electrical hazards. It's also worth noting the importance of proper installation techniques for grounding and bonding systems. Improperly installed grounding and bonding systems can be ineffective or even dangerous. Some common installation errors include using undersized grounding conductors, making loose or corroded connections, and failing to properly bond metal parts of the electrical system. To ensure proper installation, it's important to follow the manufacturer's instructions for all grounding and bonding equipment and to use appropriate tools and techniques. It's also a good idea to have grounding and bonding systems inspected by a qualified electrical inspector to verify compliance with the code. Furthermore, it's important to understand the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting the non-current carrying metal parts of the electrical system together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Grounding helps to stabilize the voltage of the electrical system and provides a path for fault current to flow back to the source. Bonding helps to prevent voltage differences between metal parts of the electrical system, which can cause electrical shock hazards. In addition to following the NEC and KEC, it's also important to stay up to date on the latest changes to the code. The NEC is updated every 3 years, and the KEC may also have periodic updates. Staying informed about the latest code changes can help you to ensure that your electrical installations are safe and compliant. There are several ways to stay up to date on code changes. One way is to subscribe to a newsletter or magazine that covers electrical codes and standards. Another way is to attend training courses or seminars on electrical codes and standards. You can also consult with a qualified electrical inspector or engineer to get clarification on specific code requirements. It is also important to understand the role of the authority having jurisdiction, or AUJ, in enforcing electrical codes. The AHJ is the governmental agency or individual that has the responsibility for enforcing electrical codes in a particular area. The AHJ may be a local building department, a state electrical board, or a federal agency. The AHJ has the authority to inspect electrical installations and to require corrections if they are not in compliance with the code. It is important to cooperate with the AHJ and to follow their instructions to ensure that your electrical installations are safe and compliant. One must also consider the impact of technology on grounding and bonding practices. As technology advances, new types of electrical equipment and systems are being developed. These new technologies may require different grounding and bonding practices than traditional electrical systems. For example, solar photovoltaic, or PV, systems and electric vehicle charging stations have specific grounding and bonding requirements that must be followed to ensure safety and prevent interference. It is important to stay informed about the grounding and bonding requirements for new technologies and to consult with qualified experts when necessary. Let's explore the role of surge protection in conjunction with grounding and bonding. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes, power grid switching, and other transient events. SPD work by diverting surge current to ground, preventing it from damaging sensitive electronic equipment. Effective grounding and bonding are essential for SPD to function properly. A low-impedance ground path is necessary to allow the surge current to flow safely to ground. Poor grounding and bonding can reduce the effectiveness of a SPD and may even cause them to fail. Therefore, it is important to ensure that grounding and bonding systems are properly installed and maintained when using SPD. Another area to consider is the grounding and bonding of sensitive electronic equipment. Sensitive electronic equipment such as computers, servers, and medical devices can be particularly vulnerable to electrical noise and interference. Proper grounding and bonding can help to reduce electrical noise and interference, improving the performance and reliability of sensitive electronic equipment. Some techniques for grounding and bonding sensitive electronic equipment include using isolated ground receptacles, installing dedicated grounding conductors, and using shielded cables. It's also crucial to understand the requirements for grounding and bonding in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Electrical equipment used in hazardous locations must be specially designed and installed to prevent ignition of the flammable substances. Grounding and bonding are particularly important in hazardous locations to minimize the risk of electrical sparks and explosions. The NEC provides detailed requirements for grounding and bonding in hazardous locations in Articles 500 through 516. Now, let's dive into the topic of grounding and bonding in healthcare facilities. Healthcare facilities have unique electrical requirements due to the presence of sensitive medical equipment and the potential for electrical shock hazards to patients. The NEC provides specific requirements for grounding and bonding in healthcare facilities in Article 517. These requirements include the use of isolated power systems in critical care areas, equip potential grounding systems to minimize voltage differences, and regular testing of grounding and bonding systems to ensure their effectiveness. Also, consider the grounding and bonding of communication systems. Communication systems, such as telephone, data, and cable television systems, can also be susceptible to grounding-related problems. Improper grounding and bonding can cause interference, noise, and even electrical shock hazards. The NEC provides requirements for grounding and bonding communication systems in Article 800. These requirements include the use of a dedicated grounding electrode for the communication system, bonding the communication system to the building's grounding system, and protecting against voltage surges. It is also essential to understand the importance of regular inspection and maintenance of grounding and bonding systems. Grounding and bonding systems can deteriorate over time due to corrosion, loose connections, and other factors. Regular inspection and maintenance can help to identify and correct problems before they lead to electrical hazards. It is recommended to have grounding and bonding systems inspected at least annually by a qualified electrical inspector. During the inspection, the inspector should check for loose connections, corrosion, and other signs of damage. The inspector should also test the resistance of the grounding system to ensure that it is within acceptable limits. Finally, always remember to prioritize safety when working with electrical systems. Electrical work can be dangerous, and it is important to take precautions to protect yourself from electrical shock and other hazards. Some safety tips for working with electrical systems include always de-energizing circuits before working on them, using appropriate personal protective equipment, such as gloves and safety glasses, and following safe work practices. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work for you. In summary, a comprehensive understanding of the NEC and KEC, along with adherence to relevant standards, proper installation techniques, and a commitment to safety, are crucial for ensuring effective grounding and bonding practices.